Okay, guys, so we're going to do something called, ignore the redness. I have shingles. I'll be fine. Luckily, I don't have to see you, so. We're going to talk about something called the ambiguous case. So let's take a look at, first of all, in ninth grade geometry, usually you'll have a teacher and they'll put up you'll have two parallel lines. Well, the question is, first of all, what are parallel lines? How do we define parallel lines? And kids might say lines that never meet. And I say no. That's not a good definition of parallel lines because, why is that a good idea? Because let's imagine a scenario where you and I'm standing here, you're standing here, let's say we're 4 meters apart. And we walk to this distance, but now we're 2 meters apart, and we walk this same distance and we're 1 meter. It's like we're walking 1 meter, we walk another 1, and we're now like a half apart. And we walk another meter, and we're now a fourth apart, right? And so it looks like the lines are going to meet, right? But we know, so 4, 2, 1, 1/2, 1/4, we know that these lines are never meeting. But those are not, once again, because of a geometric sequence, we know those lines are never meeting, but they're not parallel. So we need a more precise definition for parallel. And the definition for parallel is two lines that maintain equal distance. Parallel lines, two lines that remain at a constant distance. Okay. So we draw our two lines. Okay. We draw our two lines. Can everyone see that? Yeah, it's good. Now what we're going to do is, on the top line, I'm going to put A, and on the base here, I'm going to put BC. And the idea is that we have the area here. Because we know these two lines are parallel, we know the area is, the area is 1/2 the base times the height, correct? Now, we know the base. We know the base is BC. It's BC. The question is, what's the height? Well, this is easy. It's the distance between the parallel lines. So the base is BC, and the height is the distance between the parallel lines. Okay, and that's kind of cool. Now let me rock your mind. The kids in ninth grade, they're like, "Oh my God, Mr. Riley, that's crazy." Let's think about this for a second. I can move A anywhere. I can have, let's call this A slash. And then let's use another triangle. How about blue? And how about over here, A double? And so the question to you is, what can we say about the areas of all three triangles? And you would say they're all the same, Mr. Adler, because they all have the same base and they all have the same altitude. So you can run A over it. All the triangles all have the same area. Kind of cool. So let's move ahead. So we conclude that all three triangles have the same area. Once again, they all have the same base, they all have the same altitude. Therefore, no matter where A is, any triangle has the same area. Nice. Let's continue. What we're going to do is, I'm going to have the same parallel lines. I'm going to have the same parallel lines. I'm going to have my A, right? I'm going to have my base here. But I'm going to find the mid, so I have B, C, and A. I'm going to find the midpoint of BC. Let's move A over to the midpoint. So this is the midpoint of BC. You'll see in a second what I'm doing here. I have the midpoints, okay? And so I have one triangle here, A, B, M. Okay, and the other triangle I have is A and C. I have two triangles, and my question to you is, do these triangles have the same area? And some of you might look and I go, oh wait, let me remind you, this was the midpoint. So these bases are equal, and the heights are equal. So yeah, these two triangles they have the same area. It's kind of cool, right? Now let's bring it up to where we are, because if we apply area of a triangle, we get some really weird identity. Well, it's not weird, it's kind of interesting. So we're going to call these, we're going to conform with the letters we've used. We're going to call this B, and we're going to call this A, right? Now we've said that the areas of the triangles are same. So triangle 1 has an area of 1/2 AB. Well, let's call this C, sine C. Triangle 2 has area 1/2 AB sine of, well, if this angle is C, its supplement is 180 minus C. And since they're equal to each other, we can start to cancel. We end up with this really amazing identity, is that the sine of C is equal to the sine of 180 minus C. Now, we're going to get to this because we're going to start to find the sine of 135 and 215 and 300 and 330. That we're going around we're finding the sine, cosine, and tangent of all these angles. But right now, you just need to know that the sine of an angle is equal to the sine of its supplement. Now, where does that show up? Well, it shows up in area problems and law of sine problems. If you notice I'm sorry, I apologize. First of all, you can check this out in your calculator. Do some examples. The sine of 70, the sine of 110, the sine of 45, the sine of 135, the sine of 60, the sine of 120. Check these in your calculator and be like, oh yeah, they work. These are degrees. You can see down there? Nice. So let's get to some examples. What you might have noticed is that I never asked you to find the angle in area problems. For example, I never said, here's a triangle whose sides are 5 and 7. The area is 15. Is it 15? 12. The area is 12 centimeters squared. Find theta. I never asked you that. Because we didn't yet want to deal with the ambiguity. I wanted you to know how to do area of a triangle, but we still need to talk about the ambiguity. Well, now we understand the ambiguity, that there's two possibilities. Actually, any triangle problem with an angle issue can be solved actually with the chart I wrote, with the parallel lines. If you think about it, here's your 7, here's your 7, here's your 5, here's two triangles. So we have to find these two angles. So you can see already, okay, no big deal, Mr. Adler. Plug it in the formula. So 12 centimeters squared is equal to 1/2 5 times 7 sine of theta. Let's see, 24 divided by 35 equals sine of theta. Obviously, it's a calculator problem. We'll know, but we'll get there in a little bit when it's not going to be a calculator problem. The answer is 43.3, or 180 minus 43.3, which is 136.7. So it's kind of cool. There's actually two types of triangles that have an area of 12 and sides of 5 and 12, 7 and 5. Kind of interesting. And this should always work. When would it not work? When let's change the area. So let's let the area be 30 centimeters squared. You set up the equation. You say, okay, no, it's an ambiguous problem. I'm good. You say 30 equals 1/2 times 5 times 7 times the sine of theta. You end up with 60 over 35 equals sine of theta. Immediately you stop working on this. Does this have a solution? No, because sine cannot be greater than 1. So that's good. Now let's look at the law of sines problems. Law of sines problems are a little more elaborate, but it's no big deal. You just have to know. You have to know what's coming. You have to know. Be like, oh, law of sines ambiguous. The second they start with law of sines, you know there might be problems. But again, you always saw a problem like this, where this is 60 degrees, this is 80 degrees, this side is 14. Find x. This is a unique triangle because what you learned in geometry: angle, angle, side. Angle, angle, side is the way you prove triangles congruent. But a thing that you learn is not guarantees is something called side, side, angle. I use the bad word, angle, side, side. That's how kids remember not to use it. But whatever, teachers don't like that. Let's see, 55, 10, and 9. So, let's see. Let's call this A, B, and C. Sorry. I just used my spit to clean the board. That's really gross. Okay. So what's going on here? So in this case, we don't have an angle, angle, side. We have a side, side, angle. That's a no, because it's angle, side, side. That's a no. So no. But it's not a no that it's not possible. It's a no because we're not guaranteed a unique triangle. So we can still solve this problem. We can still have a solution. But there's a possibility that there's not going to be a unique solution. And in math, we're always interested in unique solutions. But these are a case where it's not unique. How are we going to deal with this? Well, it's still the same law of sines. So we say, fine. The sine of C over 10 is equal to the sine of 55 over 9. We manipulate it, sine of C. This is easy. I just have to get rid of the 10. Sine of C equals 10 sine of 55 over 9. We got sine of C equals, what did I do? 0.910. Do you have to do this much work if it's a calculator problem? No. But I'm old school. Like, you will find when you're working with your parents or your grandparents, like, they'll be like, oh, well, we did this, blah, blah, blah. And you're like, okay, grandpa, like, what else? But, like, we would bring it down here, and then you have to go to a table. Yeah, you can just stick this in the graphing calculator, but I work down to this. I work down to here. This is what I do. That's what I do. What do we have? So you stick it in the graphing calculator. You do the inverse sine of C. Of 0.910. And we get our two answers. We get 65.5, but we also remember that it's also, or 180 minus 65.5. And you're thinking, okay, we're done. 180 minus 60.5 is 114. 114.5. So we think we're done, though. We're not done. You're not done with. These are like just pains in your behind problems. This is what they're tedious and they want to get you on the stuff. What do we have to do now? We have to determine if these angles actually work in the triangle. We have to do like a chart. So we're like, fine. Example 1, the first angle, C is 65.5. Angle B, angle A, is 55. Add these up, 5, 0, 120, 180 minus 120.5. 59.5. So we're good for that side. The angle is 59.5. Now let's take a look at this one. The new angle is 114.5. Angle A is still 55. So let's see. A. Let's add these together. 5, 9, 6, 1. Do we have enough for another angle in there? There are cases where you don't, but in this case we do. What is that? Let's see, 180. Well, I don't need to do that. How do we get from 169 to 180 up 0.5 up 10? So angle B is 10.5 degrees. Therefore, there are two triangles. There are two triangles that have 55, 10, 9. And it looks something like this. Yeah, I guess my picture's not a good picture. I guess the idea is, I see what's going on. So this is 55. And I guess the idea is, what's the first angle? This is 9. Oh, I see. This is like, 59. Or, like this is 10. So this could be another, these could be the two triangles that represent that. Sorry. Oh, sorry. Anyway, this is the ambiguous case. Whenever you're using area of a triangle, law of sines, you're gonna get the ambiguous case issue.